Light. What is it? Where does it come from? How does it even work? Those are the sort of questions that we've been asking ourselves for thousands of years. But we didn't start to get real answers until the late 18th century and 19th century. Scientists in the 17th century were on the right track and set the basis for it to be solved later on, with Newton and his particle theory versus Huygens and virtually everyone else and the wave theory. The only mistake they made was thinking it had to be one or the other, which was a fair assumption. How can light be both made up of waves and particles? This is where quantum theory and the photoelectric effect come into play. The first recordings of the photoelectric effect came from Heinrich Hertz in 1887. Max Planck introduced Planck's constant in 1900, designing the famous E=hf formula, where E is energy, h is Planck's constant, and f is the frequency of the light. Einstein then went on to confirm that light contains quantities of light, called quanta, and this is made up of photons. That's what we think we know right now, but the beauty of science is that it could change in the future. However, we have some pretty solid proofs and evidence for it nowadays. We put together our own photoelectric effect experiment, aiming to find how Planck's constant can be calculated. The experiment basically looked like this simulation. A lamp with variable wavelength was shone upon a certain metal which ejected electrons onto an anode, and the electrons were detected by an ammeter. Keeping the metal constant, we changed the wavelength of light, recorded the stopping voltage of each wavelength. The frequency of the light was graphed against the stopping voltage and a trend line was found. The gradient of said trend line was also the approximate value of Planck's constant, and our value of 6.4 times 10 to the negative 34 has an error of only 3% compared to the universally accepted value of 6.63 times 10 to the negative 34, giving some validity to the experiment. This experiment is known as the photoelectric effect. But what does this all mean? The fact that electrons were emitted from the metal meant that particles had to be emitted from the light source to cause the metal to shoot out electrons. And we already know that light can also act as a wave because it refracts, reflects, and diffracts just like any other wave, thus proving that light is made of particles and waves. Newton and Huygens were very close. They gathered their own research and drew conclusions to point out their own idea of the nature of light. But they made the simple mistake of assuming life as we know it acts on the same scale as life on the quantum scale.